Hello students, today we will see the last rule for drawing root locus along with the steps that we will be using for drawing root locus. Okay, so rule number 8 is actually the intersection with imaginary axis. Intersection with imaginary axis, that is called as j omega crossover. Please remember this words j omega crossover. Okay, so when root locus is intersecting with j omega axis, or I will say the point at which root locus is intersecting j omega axis. Just take an example. Suppose this is sigma j omega axis and I am drawing the root locus like this. Let's just imagine this is our root locus. So this root locus is intersecting j omega axis at this point. Okay, so this point is called as j omega crossover. Okay, so what is the method to calculate j omega crossover? That is nothing but the Routh's array. Okay, we know that step number 1 for calculating Routh's array we need a characteristic equation. Okay, suppose transfer function is there, then you can calculate characteristic equation from the transfer function by substituting the value of g of s and h of s here. Okay, then step number 2, apply Routh's array in terms of k. Okay, if that transfer function is in terms of k, so definitely your characteristic equation it will be in terms of k. So we know that how to form the Routh array. Okay, so what we will do, first 2 rows it will be from the characteristic equation and the remaining rows we need to put using the formula, and last term, that is s raised to power 0 element, it will be again from the characteristic equation. Okay, step number 3, determine k marginal. Okay, so we know that from Routh Stability Criteria what we are doing, we are assuming the first column of Routh array. Okay, for system to be stable, all the elements in first column of Routh array should be positive. Okay, there should not be any sign changes. In that case, suppose any term is in terms of k, so what we are doing there, we are assuming that this k is positive. Okay, then only you can calculate k marginal. Let's assume suppose that any row is 0, then we know that we are just calculating auxiliary equation from the row just above that 0th row. So same step is here. Okay, this step will be more clear when we will solve numericals, but this is exactly the same whatever we have solved in stability analysis. Okay, so then we have to make the auxiliary equation. Then step 5, derive the roots of auxiliary equation. We know that auxiliary equation is there. Okay, so depending on the order of the auxiliary equation you will get roots. Suppose the auxiliary equation is the quadratic, that is second order term, then you will get 2 roots. Okay, so derive the roots of auxiliary equation. These roots are nothing but j omega crossover. Okay, you can see that whatever roots you will get, that roots will be always imaginary. Then only, or I will say the points or the roots whatever I am getting, that will be imaginary. Okay, so that roots or that point is called as j omega crossover. Okay, or intersection point of the root locus with imaginary axis. This is imaginary axis. So this is intersection of root locus with imaginary axis is called as j omega crossover. Okay, so this is actually the last step or last rule for drawing root locus. Okay, so now we will see these steps for solving problems on root locus. So actually we are revising all the rules whatever we have completed, or we have started from rule number 1 to 8. Okay, so here I have not written, but when I have started I told you that root locus is always symmetrical about real axis. Okay, I have given example and we have discussed that root locus will always symmetrical about real axis. Please remember. Then from the transfer function, see here step number 1, from the transfer function what you need to do, you have to find number of poles and number of zeros. Okay, so we know that that is actually the rule number 1, and we have solved this step number 1 or rule number 1 with example. So we know that pole is represented with n and 0 is represented with m. Okay, so see, suppose I am assuming the transfer function as, just I am taking the example s plus 3, s plus 6. Okay, suppose this transfer function is there. So we know that in this transfer function all are the real poles. Okay, so see here what will be my n will be 3 and n will be 0. Okay, so what I will do, we have calculated number of loci, that is total number of root locus. So we know that as n is greater than m, okay, so there will be 3 root locus. Okay, so whichever is greater, suppose m is greater, so what we will do, total number of root locus, it will be equal to n. Suppose n is greater, so total number of root locus, it will be equal to n. So here we know that n is 3, so total number of root locus is equal to 3. Okay, then part B is find number of loci ending at infinity, or I will say terminating at infinity. Okay, so see, we have studied that root locus will always start from pole and it will terminate at 0 if it is present, and if 0 is not there, so it will terminate at infinity. Okay, see, in this transfer function 3 poles are there. Okay, so root locus will start from the pole and it will terminate at 0, but in this transfer function as 0 is not there or zeros are not there. Okay, so all these 3 root locus will terminate at infinity. Okay, so here number of root locus terminating at infinity, it will be 3. Okay, see, suppose any 0 is there, in that case out of the 3 root locus, one of the root locus may terminate on 0 and remaining 2 will terminate at infinity, as there are no zeros to terminate. Okay, see, this point will get clear when we will solve more numericals. Okay, step number 2, find real axis loci, that is region on root locus. So if you remember this rule, what we did, we have plotted the transfer function in S domain. So here I will plot S is equal to 0, suppose this is minus 3 and third is minus 6. Okay, so as no zeros are there, so what we did here, we have considered the region. Okay, so this region will give you, this region is nothing but it will give you the part from where the root locus will pass. Okay, or I will say this is the region on the root locus, but this region is actually real axis region. Okay, so let's see here, I am considering the point P here. Okay, so we know that what we are doing, we are calculating or we are doing addition, that is number of poles and zeros on the right hand side of this point P1. If that addition is odd, then that will be the region on root locus. So we can check that here only one pole is there on the right hand side of this point P. Okay, so what I will say, from this pole to this pole, 0 to minus 3, this will be part of region on root locus. Okay, then see here I am considering point P2 in between minus 3 to minus 6. Okay, so see here on right hand side of P2 2 poles are there, so addition is even, so this will not be part of region on root locus. Suppose I am considering point P3 here. Okay, so up to infinity, see here the number of poles and zeros on right hand side of this P3 is actually odd, 1 2 3. So this will be the region on root locus. Okay, so for this transfer function we have 2 regions, from 0 to minus 3 and from minus 3 and from minus 6 to infinity. Okay, and from minus 6 to infinity there will be 2 regions. Okay, then step number 3, find number of asymptotes and their angle. Okay, so we know that number of asymptotes is equal to n minus m, this is given with this n minus m, where angle is given with the formula 2x plus 1 into 180 upon n minus m. Okay, so please remember this formula, we have already taken in the previous lectures. So this is actually the formula, beta is equal to 2x plus 1 into 180 upon n minus m. Okay, so see here, for suppose I am considering this transfer function, so definitely here n minus m will be 3. Okay, so number of asymptotes here, it will be 3. Okay, and there will be 3 angles, because here I will be considering x is equal to 0 1 2. Okay, so accordingly I will calculate beta 1 beta 2 beta 3. Okay, then step number 4, find center of asymptotes, that is sigma c. Okay, so sigma c is nothing but summation of real part of poles minus summation of real part of 0 upon n minus m. Okay, if you remember the formula, summation of real part of pole minus summation of real part of 0 upon n minus m. See, this is actually real part of poles. Okay, summation of real parts, we have to consider only real part. Okay, then step number 5, find breakaway or break-in point that is denoted with sigma b. Okay, so if if I will say the adjacent poles or adjacent zeros are there, in that case you need to calculate breakaway oblique break-in point. For two adjacent poles we are calculating breakaway point, for two adjacent zeros we are calculating break-in point. Okay, so we need to calculate valid breakaway point, whatever roots or point we are getting, so that point should locate on the region on root locus, then only we are saying the valid breakaway point. Step number 6, for complex poles and zeros find phi d phi a. In previous lecture we have seen phi d and phi a is generally calculated if complex poles and complex zeros are present. In this transfer function you can see that all are the real poles. Okay, so for this transfer function no need to calculate this step. Okay, so this step is calculated only for complex poles and zeros. Step number 7, find j omega crossover if locus crosses j omega axis. Okay, so this is the step number 7 is nothing but rule number 8 actually. Okay, if the root locus crosses j omega axis, then that point we need to calculate, that is called as j omega crossover. Okay, so step number 8, last step, is actually predict stability of the system. The purpose of drawing this root locus is to predict on the stability. Okay, so if we know that if the poles and zeros are located on left hand side of j omega axis, so definitely system will be stable. But here, as we know that if k is changing, we are getting the graphical representation. Okay, so from that representation, from that drawing, we can calculate we can comment on the stability. Okay, so students, I hope you got the rule number 8 and the steps for drawing root locus. Thank you.